trim it away to match the obstacles. We've got efficient algorithms for that. We can fly mat-led planes through forests. We can do it directly on the trigonometric verification, or we can do Taylor expansions. It turns out the Taylor expansions aren't that bad, so we do them a lot in practice. This one, like I said, I'm really proud of being able to do it, regions of attraction analysis for limit cycles. So we do it with a construction that basically designs a moving coordinate frame around some periodic trajectory and create a Lyapunov function on that moving coordinate frame. I'll spare the details, but it's still a Lyapunov analysis. The Lyapunov candidates are still generated with the Riccati equation, and we can handle hybrid dynamics in this too, as long as our constructed coordinates line up with any switching surfaces. Thought about that, if that makes sense. And what it gives me the ability to do is, for instance, take my walking robots. This is one of the simplest walking robots we think about. It's called the compass gate. It's got just 2 legs, straight legs, pin joint at the top. But it's cool because you can put it on the top of a small ramp, give it a push, and without any torque, it's just a passive walker. It'll walk stably down a small ramp. This is one of the examples of passive dynamic walking. And it does it with relatively few assumptions. You just assume that the torque, there's no, well, we can put torque in the hip, but this one had no torque. We just assume that there's pin joints and hybrid transitions for the feet. Okay, so that robot, if you will, it has no controller in it, but that robot undergoes a stable periodic motion that's punctuated by these hybrid impacts. Every time the foot hits the ground, there's an instantaneous change in velocity. The legs switch from the left leg being the stance leg to the right leg being the stance leg, and then it repeats. Okay? And we knew that the region of attraction, there was some region of attraction of this from the passive system, but we couldn't compute it. But now we can with this construction. We can efficiently underestimate the region of attraction of these hybrid limit cycles. What's particularly cool about it is the compass gate is hard enough. Most walking robots are hard enough. You can't actually solve in closed form for that periodic cycle. I can't integrate the return map of the system. I can't do analytic computations on these walking robots in general. But it turns out even if we use a numerical approximation of the periodic trajectory initially, I can still get an exact verification, analytic verification of these regions around the trajectories. So it allows us to do formal analysis on limits like this, even when we can't integrate the dynamics of the system. All right, so that's the first piece. I wanted to tell you about this idea of using optimization to compute Lyapunov functions. It works pretty well. So the scaling is polynomial in the number of decision variables. The decision